All right, hi everyone. Welcome to the problem session. This is the problem session number 10 for the HOT. Uh, Today is the 11th of August, 2022. So I'm just going to be going over, I think I'll do problems 1, 2, 4, and 6. And by the way, feel free to chime in if you can't hear me or anything like that. And yeah, so I'll do 1, 2, 4, and 6. I think in the Euro session on Artem did I think 1, 2, 3, 4, and 5. So hopefully that covers kind of all of the yeah, all these pretty well. And I think we're going to be posting both recordings, but don't quote me on that. So, but before I do, I wanted to kind of give a brief recap of what's the whole deal with this propositional truncation thing, which is kind of the big theme of the most recent lecture and this problem set. So, and yeah, feel free to interrupt me if you have any questions or anything doesn't make sense or whatever. So the idea of propositional truncation is kind of realizing that here is our universe of types. And then living within this universe, we have a subuniverse of propositions. So remember, we defined a proposition to be a type that such that every element of that type is equal to every other element of that type. So up to identity, there's a unique element of a proposition, or a proposition can be empty. So those are kind of two propositions, and the so but not all types of propositions. There's a lot of types out there that are not propositions. And so the idea of propositional truncation is we're going to do what's called reflecting this broader universe into our subuniverse of propositions. And so what that kind of looks like more expressly. So I'll go ahead and write the universal property of propositional truncations, and then yeah, and then kind of unpack a little bit what it means. So we say that so we're going to assume that our type theory comes equipped with propositional truncations. So we're going to say for every type type A, so A here could be any type at all. We have a type which we call the propositional truncation of A, which we write as these double brackets A, which is a proposition. And sorry, by the way, if my voice is a little bit croaky, I'm just getting over a cold, so hopefully I don't need to cough or anything. But so this prop is so saying that the truncation of A is a prop says two things: A, that or first of all that this is a type, and second of all that this type is a proposition. So we have a witness of is prop of the truncation of A, which remember is the same thing as sigma proof that for all x of type truncation of A, and or sorry, for all x and x prime of type truncation of A, we have x equals x prime. So it's a proposition. And so not only do we want to be able to take any type and turn it into a proposition, we want this this truncation to have some special properties. And so we're really concerned with what we're going to call eta, a map eta from A into the truncation of A. Excuse me. Which will also write eta of A. We'll write that as single bars A. And so this is an element of A for any A. And so when we have this map, then one thing we can do is we can form this the map of precomposition with eta. And so if I do, we can write that as something after eta, which in general this will take any type from well, let's do it as yeah, so any a into some other type q. So if I have a something from yeah, so if I have a map from a to q, or sorry, no, I want this to be truncation of a to q. So I have a map from the truncation of a to q, then I can precompose it with eta, and I get a map from a. So this we can form in general, and we say the universal property of the truncation is that this operation of precomposition is an equivalence whenever Q is a prop.
We can't see the bottom of the paper.
Oh, sorry. Thank you. So yeah, this so we can form this precomposition map in general, but
sorry, could you raise it up just a little bit more?
A little bit more. All right.
There we go. Good.
Yeah, sure. I'm sorry. I'll try to keep it further. Yeah. So the idea here is that we have this precomposition map in general, but if the Q that we're mapping into happens to also be a proposition, then this is going to be an equivalence. And so let me just kind of for our general understanding, let me spell out a little bit what that means. So remember that an equivalence is a contractible map. So so to say that this map here is an equivalence is to say that for everything in its codomain, which I will graph it. So for everything in its codomain, the fiber of that element under this map is contractible. That's equivalent to. We prove that that's the same thing as being an equivalence. And so we have that. So kind of rephrasing this, that's why I got this universal property. This says that for every map, which I'll write as F from A into Q, there exists a unique map that maps to F. So yeah, so for everything in its codomain, its fiber is contractible. So write that as is contour of the maps alpha is F prime from truncation of A to Q, such that if I apply this map, this precomposition map, I get F. So such that F prime after eta equals F. So kind of the picture to draw here is that, so I actually draw this on an earlier diagram here. So this is trying to arrange everything so it's visible. So this is our condition this is our universal property that the precomposition eta map is an equivalence, namely it has contractible fibers. And so what this says is that if I have any type A here, so A is in general not a proposition, and let me also add the side condition here that Q is a prop. Or actually, we could even make that part of the quantification for all Q prop. And so, yeah, so for any, so we have our A here, which in general is not a proposition, and then we have any proposition Q. And so then the data of the propositional truncation gives us this proposition truncation of A and this map eta. And so what the universal property says is that for any F here, this is our F, for any F, there exists the unique map here, which is our F part. Which is kind of you can think of this as kind of the truncation of F. It's taking F, which might have one endpoint outside of prop, and it's collapsing it down into being a implication between propositions. Okay, is this all clear? Everyone, yeah, relatively on the same page about propositions and propositional truncation? All right. Okay, so there's just a couple things I wanted to mention about what this means. So, kind of interpreting this condition here, what this says is that defining a map, or yeah, it's so kind of how we're going to use this universal property is by assuming that whenever we're trying to map out of propositional truncation, that all of the things that we're mapping with are of the form this eta, are obtained by applying this eta. And so, yeah. Check one thing. Yeah, so you can kind of see why that is in this universal property. That if I'm trying to map, so if we're trying to obtain a map from the truncation of A into Q, so we're trying to prove a proposition Q with an assumption of truncated A, then what we can do is we can essentially assume we have an element of so yeah, we can construct a map like this. So we just say if we have some A, then we produce a Q, and then we can recompose, or yeah, we can use this equivalence, so we can go back to a truncation of A to Q. So I'll kind of show what that looks like when we do a problem in just a second. All right. Yeah. Okay. Let's. That's enough. I think prelude. So let's go ahead and start solving some of these problems. So I said I'm going to do 1, 2, 4, and 6. So let's go ahead and start with 1, and that'll, I think, kind of give us a good opportunity to kind of get our hands dirty a little bit with these propositional truncations. So the first one, so 1A, says we want to prove that there is by implication, a equivalence between A and double truncated A. And so we wrote this as this just double arrow instead of as an equivalent sign. because both of these are propositions. So remember that a proposition, there's if you have a map whose codomain is a proposition, then there's at most one such map, because this is a proposition, so we could intuitively think of this as having either 0 or 1 elements, and so therefore, there's not multiple ways to map into this type. And similarly here, this is a proposition, so there can only be at most one map going in each direction. And so if we manage to, and so you can do a quick little proof to show that if you have a map from left to right and right to left, then that has to be an equivalence. So they both have to compose to be the identities. And so in order to prove this, we just need to construct a map from left to right and right to left. So, right to left, I'm going to call, left to right, I'm going to call this unbox. And so unbox is going to go from the truncation of A to truncation of A. And so this this is where our universal property comes in, is that we are trying to construct a map from we're trying to construct a map from the truncation of A, so a truncated type, into a proposition. So here, sorry, there's a little bit of notation, a little bit of a clash here, but this brackets A here is a proposition, so that's going to stand in for a proposition Q. So if we want to construct something of truncation A into Q, which is truncation A, then we just need to get something from truncation A into Q, which is truncation A. So sorry if that was a little bit unclear, but so this is how we write this is how we write functions dealing with truncations, is we say that since this is a brackets A is a proposition, so we want to say what is unbox of some like K. So K is a truncation of truncation A. Since A is a proposition, we can assume that K is of the form truncation of some K prime, where K prime is. So this is how we use the universal property, is that if we're trying to map into a proposition, then we can kind of unbox this and assume that we can get some K prime, which is like the thing sitting inside this truncation. So this can be a little bit weird to get used to if you're not too familiar with it, but once we kind of do some of these these examples, you kind of see with when it's okay to do this. But the thing to remember is that your codomain needs to be a proposition, and then you can kind of assume you're working with if your codomain is a proposition, then you can kind of assume you're working with the data of the type that's truncated, and then you can use this universal property to uniquely get a map out of the truncation of what you want. Okay, so we can assume that. So this gives us access to this K prime, which is a term of type truncation A, and so we can say that the unbox of let me write it down here. So the color. We can say that unbox of truncation K prime is K prime, because that's of the correct mode of domain type. So there's a question: why do we right now just simple bars to enclose K prime. So yeah, I kind of suppressed this a little bit in this notation, but remember that the eta that we were dealing with, that's the single bars. So that takes something of some little a of the type we're truncating and sticks it into sticks it into the truncated version. So double bars is an operation on types. So A is a type, and double bars A is a type, whereas the single bars is this operation which takes things in our untruncated type and puts them into the truncated type. And you can kind of think of this logically as that this implies that this says that if A is inhabited, then the truncation of A is inhabited, because if I have some inhabitant of A, I can stick it into the truncation of A. And so, yeah, that's kind of how to think of the proposition of truncation is it's a proposition, so it has either 0 or 1 elements, and it has 1 element if A is inhabited, because I can stick an element of A into the truncation of A. Whereas if A itself is empty, then the truncation of A is also going to be empty. But yeah, so the single bars refers to this operation on elements, and so yeah, when we yes, what we're trying to do here is we're trying to do a map from truncation of truncation A into some Q, and so what we do is we work with the untruncated, so just one truncation of A into Q, and then we know that we can recover. So if we define a function here, then we can recover a unique function here. And so that's what we're doing, is we're really writing a function from we're kind of writing a function from truncation of A to truncation of A, which takes K prime to K prime, and then we're passing that through the universal property. Okay, so that's one direction, and then the other direction is easier. So this is truncation of A to truncation of A to truncation of A, and then this the other direction is going from the truncation into the double truncation, and so, but that's easy. We can just put box, so to undo box, unbox is box, and that can just be eta. So box of some K prime, which is in the truncation of A, is we just stick it inside a truncation. So this is in truncation A. And so that does what we want. And then again, like I said, these are both propositions. So if I have a function in both directions, then this has to be an equivalence. So we get that the double truncation is the same thing as the truncation. Those of you who know some functional programming might recognize this as a monad. So this we're proving one of the monad laws for the truncation proposition truncation. So so some of the terminology is motivated by that, specifically this eta, so this is also a monad law. So that helps. Okay, let's do a little bit more of an elaborate example. And so that'll be 1b. And so 1b asks us to prove that if there exists, or if there merely exists, we might say, there merely exists an x in A such that b of x is inhabited. So the truncation of b of x, so we know that there's some inhabited, but we don't have any particular one. That's the same as saying that there constructively exists an x in A such that b of x, and truncating that. Okay, and I think this was a point that came up in lecture yesterday. Can we move the truncation bars inside the sigma? And we can, but we just have to make this a constructive, or sorry, a truncated. There exists. So remember that there exists an x of type A such that B of X is just defined as the propositional truncation of there exists a X in A such that B of X. I think I got that right. I always get this wrong. 1 second. Yeah, I think that's right. Okay, so yeah, so this will provide us even more opportunities to work with these truncated types, because so existence is defined in terms of truncation. Both these are truncations. So first thing to note is that these are both propositions. So both sides are propositions. So we don't need to, so we can just define a map in one direction and a map in the other direction, and we don't need to check that they commute to the identity or anything. And then we also, this both sides being props, that's going to make it a lot easier for us, because we can use our propositional our units of property of propositional truncations. Okay, so let's go from left to right. So we have yeah, so let's go left to right. So we need to go from so yeah, let me write this. So our left to right, which I'll call left to right, needs to take something of this type. So I'll spell that out as the truncation of sigma X in A, and then we also have a truncation on the B of X. And that goes into the proposition of the truncated of sigma X B of X. Okay, so again, we're going to use, so our codomain is a proposition, so we can use our universal property, and so we can work with a, so we can assume we're given an X in type A, and a notation to what I don't really use, BX. So BX, which says that merely B of X. And so we want to, we want to put something into this type. Now our again, our codomain is a proposition, and so we can again apply this recursion principle for propositional truncation to this BX, and so we'll get some B prime of X, which is of not truncated, of type B of X. So here it's kind of really just a process of making sure we're getting the right, we're doing these kinds of unboxings right, and always checking that our codomain is a proposition. And then once we kind of extract out all this data, then we can go ahead and then it's really easy. We can just say that once we extracted all this, LTR of so this is so we're going to write this as it's the propositional truncation of X with the propositional truncation of B prime X. Does that make sense? Is just you just kind of rearrange the data as X and B prime X. So kind of the only interesting thing we're doing here is taking just doing this recursion thing twice to get rid of this interior truncation. Does that make sense? Yeah, so there's a comment about I use do notation. So yeah, if you're used to kind of Haskell style monadic programming, then you can write some of these as a do block for your monad. So that's fun. Okay, and then I think the other direction is relatively similar. For going back this way, then it's even a little bit easier that you're mapping again to a proposition, so you just so you extract this x and b prime x, and then you just need to put it together in this way in order to get something of this type, and it's all done. Okay. So in the interests of time, I think I will skip 1C and D. We can come back to them if there's interest, but I wanted to make sure to get to some of the more challenging problems, and so maybe we'll leave those and come back to them. But let's move on to 2. I think 2 is a good exercise. So in 2, we're referring to this idea. So when Egbert defined propositional truncations in lecture, he didn't do it immediately like this. So here I'm spelling out. I'm saying there's the propositional truncation, and but that's not exactly how Egbert defined it in lecture. So how he defined it was that we can, given a piece of data like this, like a type and a map like this, that we can say that pair is a propositional truncation for A if it satisfies this universal property. So let's spell that out. We said that so if we fix some type A, then P, so a P, which is a prop, and a map F from A, from A into P. So this is a propositional truncation of A, but propositional truncation of A if we have this property again, the precomposition with F, so that goes from P into Q into A into Q is an equivalence for any Q. So they're just kind of rephrasing the same things as just rephrasing it as a property. But then I've been saying that we fixed a particular propositional truncation of A, which we're calling bracket A eta, which satisfies this property. And so the reason that it's justified to use the word the in this context is that we have the 3 for 2 property. So if I have A and I have F P, and then I have F prime and P prime. So these are the so these three conditions. One is that PF is a prop trunk. Two was that P prime F prime is a prop trunk. And three is that P is equivalent to P prime. And since P and P prime are both propositions, then this equivalence is going to commute with this F and this F prime. So we get a equivalence here. If both of these are propositional truncations, then we get an equivalence here, and F after the equivalent, or the equivalence after F, and has to be equal to F prime, and the F prime followed by the equivalence has to be equal to F, because these are both propositions. All right. So yeah, this was the 3 for 2 property, and we like 3 for 2 properties in this area, these kind of areas of math, because they're helpful. So the so now what question 2 asks us is to basically, this is asking us to prove that propositional truncations are preserved products, preserved binary products. So it's saying that so if I have a so here P and Q are propositions, A and B are types, and F goes from A into P, and G goes from B into Q. And so the first thing I can do is I can form this map F cross G, which goes from A cross B into P cross Q. That does the thing you kind of expect. G of AB is FA and GB, of course. So the claim is that if F is a propositional truncation of A and G is a propositional truncation, BG is a G is a G and Q is a propositional truncation of B, then this is a propositional truncation of A times B. Okay, so basically what we have that precomposition by F is equivalence, and precomposition by G is an equivalence when the codomains are propositions. And what we want is that precomposition by F times G is equivalence from when the codomains are propositions. Okay, everyone understand the statement? All right. So let's go ahead and have into doing it. So the idea here, so we fix some, let R be a proposition. And so then we have postcomposition by F times G. That takes so that takes a map from P times Q into R and turns it into a map from A times B to R. And so we want to construct an inverse for this. And the nice thing to note is that this does that show up late? This is a problem. Oh yes, thank you for noting. Yeah, this is not times. This should be certain. So this right here is a proposition, and so we want to construct an inverse for this. And actually, this is also going to be a proposition for the same reason, namely that whenever you're mapping into a proposition, if you have like an arrow type like this, and the codomain is a proposition, then it's going to be then the whole thing is a proposition. So R is a proposition, so that makes A times B arrow R into a proposition, and likewise here. So I think this is a fact that was proved, or I think we proved it in more generality that if you have a pi type into a family whose fibers are propositions, then you get then that pi type is a proposition. And this ultimately links to the reason that we don't have to use propositional truncation in the definition of for all between propositions, like we had to remember exists, we had to truncate, but for all we didn't, and that's because for all, if you're mapping into propositions, then you get propositions. Okay, so we want to map so since these are propositions, then any map from things of this type to things of this type will do. I don't need to check any kind of commuting to the identity kind of conditions. I just need to supply some map here. So I want I'll call it F, I guess, capital F. So we want to have F from A times B into R into P times Q. Okay, so we have F of so wait, let me check I'm going about this the right way. I realize I'm clashing with the notation of the map. So let's not give this a name. So we're trying to do so we want some of this type. We want a map of this type. And so let's assume we're given an F. So this is matching the notation of the solutions. We're given an F from A times B arrow R. So this is you kind of think this as this is a proposition valued function on R. And then then we're also given something of type P times Q. So so we'll also have assume we have a P and a little p and a little q of type P times Q. So technically we're doing the induction on product types here to assume that an element of this type is of the form of the pair, but I think we're pretty used to that by this point. And so now we just need to construct an element of R. And so the kind of trick that's mentioned in the solutions is that we can instantiate our universal property of F using the type Q arrow R. So going back to what we have that this the precomposition with F is an equivalence whenever our codomain is a proposition. And so let's take the proposition Q arrow R. That's a proposition. And so therefore we get that precomposing with F, which goes from, that's right, so F, so this is going to go P arrow, the type I'm mapping into Q arrow R, and then precompose with F, so that gives me a type A arrow Q arrow R. And so this is an equivalence. And so that's just applying the universal property of F as a propositional truncation. And so if I want to, so notice that if I have something of type P arrow Q arrow R, then I can get a Q arrow R. Or sorry, I can get a thing of type R because I have a P and a Q. So the reason I want to use this is that I'm going to define something of this type, A arrow Q arrow R, and then I'm going to use the universal property to turn that into a P arrow Q arrow R, and so then I can apply that to my P and my Q to get the R, which is what I want at the end of the day. Okay, so so now our objective is to make something of this type. And so so yeah, so we want to yeah, so what we'll do, so now we want a map of type A arrow Q arrow R. And so now we can assume that we're given an A in type A, and so now we just need to produce a Q arrow R. And let's also assume a Q prime of type Q. So now we don't need a Q arrow R. Now we just need to still produce an R. So it might kind of seem like we're going in circles, but we've done something important here in that we've introduced this A into our context. And so now what we'll do is we'll do the same trick but for G. So notice that we haven't used G, we haven't used that it's a propositional truncation, so that should be assigned to us that we'll need to use that at some point. So we're going to do the same kind of trick here, but now we're going to use now we have this A available to us. Sorry, was there a did I hear someone or no questions? Okay. All right. So the so now we we're going to instantiate the universal property of G with the proposition we're mapping into being P arrow R. And so since G is since this is a proposition, then the precomposition with G, which goes from in this case it'll be Q arrow P arrow R to so this will be B arrow P arrow R. Okay, so we're almost there. So now what we need to do so this is an equivalence. And so if we want to get a so what we'll do is we will construct something of type B arrow P arrow R, and then we'll use that to get something of type Q arrow P arrow R, and then sorry, I'm confused myself a little bit here. Yeah, so we will so the the reason we want to so now we instead of defining this, we're going to define this, and so that's going to allow us to take in an argument of B of type B. So we're trying to now our goal is to do B and P of R, and so we take in B and P prime of P, and so now we just need to again we still need to produce R, but now we finally reach where we want to get to, because now we have a B and an A in context, and so we can apply our F, which accepts those two things. So now F is of type, or F of A, sorry, you probably can't see that. So now F of AB, that is a term of type R. Okay, so now we have to kind of wind this backwards. So so what we've done is in this context we've given a B and a P prime, a B and P prime, we produced an R, and so therefore we've given a function B arrow P arrow R, and so therefore therefore we have we have this function, we have a function Q arrow P arrow R, and we have then kind of winding back, we have we have a Q, we have a Q in Q prime in context, and actually we have a Q and a P, and so we can apply that Q and that P to get this R, and then so now we have so then we constructed an A arrow Q arrow R, so we can wind that back to P arrow Q arrow R, and then we can apply so now we have a P arrow Q arrow R, so we can apply that to P and a Q, and we get an R. So sorry, so it's a little bit of a kind of a crazy mind game of context and stuff. So yeah, you might find it easier to try to do something like this in Agda, where you kind of have these contexts taken care of for you. But the point is that we eventually introduced all the things we needed, and we eventually worked backwards through all these isomorphisms, and so we have given F from A times B arrow R, we've constructed a P times Q arrow R, and so that's our proof. Questions about that? That was kind of a weird proof, but hopefully it made some sense. Okay, so then type, then B is part B is part 2B is real quick. So we want to, so it asks us to conclude that the truncation of A times B is equivalent to the truncation of A times the truncation of B. But this is pretty immediate from part A, because we showed in part A that since truncation of A is the truncation for A, and truncation of B is a truncation for B, and so they're the right things to be stand in for P and Q and F and G in in part A. And so what we proved in part A is that so this is going to be eta A times eta B. That has the universal property. This has the universal property for the truncation of A times B. But what also has the truncation for A times B is eta A times B with the usual just the truncation applied to the product. And so the 3 for 2 property, remember, says that if these two are both truncations, excuse me, then this is an equivalence. So we have an equivalence here. And again, these are propositions, so that's just kind of by implication. But we get our so that's the same thing as A times B. If and only if times B, because these are both propositions. All right. So I only have about another half an hour, so there's a chance I won't be able to get through both 4 and 6. Do people have a preference between the two that they would rather see, or because if not, I'll just try to do them both in order. Okay, seeing one request for 6. I guess since Arden covered 4, 4 is really interesting, I think, but we come back to it. But let's start with 6. Were there any questions at this point, by the way? Okay, hearing none, seeing none. Let me. Okay. So 6. 6 has a number of moving parts, but I think we can make sense of it. So the key definition of 6 is this idea of the inverse image. So the inverse image of a map is kind of like the fiber, but it's a little bit different. Namely, that it's using the truncated it's using this truncated existence instead of the usual sigma type. So here's the I'm not sure I really like the notation in MF, but we'll do that. So in is that visible? That's a little bit. So in M of F. So here F is some F from X to Y, where X is finite. And I'll say what that means, and I'll remind you what that means in a second. But we can do this definition regardless of whether X is finite or not. So if Y, little y, is a term of type big Y, then we could take the inverse image, pre-image of little y, and that is going to be defined, so definitional equality, as there exists a x in x such that that maps to f of x. So this is there merely exists something in its fiber. So this is a propositional version of it's worth noting that this will produce a proposition and did I miss a? Oh yeah. And so there's two parts. So first of all, part A asks that if this question, is this the same as the propositional truncation of the fiber? I believe so, yes. So I think we'll spell that out in a minute, but yeah, we're reminding ourselves that exists x and x such that f of x, y, that's the truncation of sigma x in x f of x equals 1. So that's the same thing. And yeah, this is the fiber of y. So yeah, it's the truncation of the fiber. Okay, so so part A asks us that say that if y has decidable equality, which I'll remind you what that means in a second. Decidable equality, then we want to prove that the inverse image f is decidable. So we'll review that. So let's kind of dig into this statement a little bit. So y has decidable equality. So color coordinate this. So y has decidable equality. Well, right here in green. So what it means to have decidable equality is that for every little y in y and every y prime in y, we either have y equals y prime, or we have a proof of not y equals y prime. And so, as we touched on, this is a remarkable property that not all types share. So, in particular, in homotopy type theory, we're interested in types that numerous types that don't have propositional equality, decidable equality. But yeah, we're assuming that y here does. So that for any pair of elements, then I can so if we need to refer to this, we'll call it like dec decidable equality or something like that for y. So dec eq for any y prime, it'll either give me a proof that y is equal to y prime, an element of that identity type, or it will give me a proof that that identity type is empty. Okay, so that's the first definition we need to make sense of this claim. The second one is that this point that this image of f is, or the inverse image of f is decidable. So it's worth noting that in f that has type y arrow prop. So remember, so y has decidable equality. So that means that part of what that means is that f of x is equal to y, and that's going to be a proposition. And so I am existentially quantifying or using this exists, which is a truncated one. So so actually, regardless of whether f of x is equal to y is a proposition or not, then this is defined using a truncation. So this is going to be always a proposition. And so for each y in M of y, is a proposition. So we have this as a predicate, if you will. It's a proposition. It's a proposition index over a type. And so what it means for such a predicate to be decidable is that so I'll say like decidable inverse images in or something like that. I don't know if I'll actually need these names, but that says that for any y and y, either in m f of y or not in m f of y. So so for every element of y, we either have a proof that there exists something in the pre-image of y, or we have a proof that there is not, that the pre-image of y is empty. Okay, so now the solutions do this one simplifying trick, which I think is good, and that we'll also want to do. And so that is restricting what it means, restricting x instead of just being an arbitrary finite set to being a particular one of our given finite sets. So let me expand on that a little bit. So remember, the idea here is that so we claim that we want that x to be finite. We demand that as part of the conditions of our theorem. And so what that means, so remember that is finite of some type x is the statement that that there exists a natural number such that merely x is equivalent to the finite set of n. And so let me note that I'll for fine n, I'll take that to be roughly the types of the type of 0, 1, ... n minus 1. So that's what I'm kind of taking fin n to be defined as. Okay, so a set is finite if there merely exists a natural number such that there exists a natural number such that x is equivalent to the finite set of natural numbers, or of n finite n set. And so we truncate this with its equivalence because we don't want to encode the information about, because if we had this isomorphism on hand, this equivalence on hand, then that would put the elements of x in some finite in some order, because these numbers in the finite, this is an ordered set. 0 is less than 1, 1 is less than 2, and so this would kind of pick a particular order on the elements of x. And we don't want that. We just want to know that x is in bijection with the set of n. We don't actually care about what the bijection is, and so we truncate this. And since x can only be equivalent to one given natural number, it actually doesn't matter whether we use the this exists or if we do sigma type. As long as this is truncated, it doesn't matter which of these we use. Okay, and so we say that x is finite, which means that it's going to be equivalent, or it's going to be merely equivalent to some natural number n. And so what we're going to do is we are going to assume it suffices to prove this prove this property for any finite set. It suffices to do it when X is just of the form fin of n for some n. For some n. So rather than just carrying around the assumption that X is finite and just kind of dancing around this equivalence with and doing all that, what I'm going to do is I'm just going to assume that X is this fin n set and prove the result I want. Prove this statement using X is equal to fin n, and then you can check through the details that you can do the same kind of propositional truncation thing to extract this. Since we're dealing with propositions all around, you can extract this actual isomorphism and then kind of use that to argue if X is just some finite set rather than these specific finite sets that we've chosen. But so it's going to make our lives a lot easier in this proof if X is just fin n for some number n. Does that make sense to everyone? Okay. Yeah, so the question like that doesn't matter from problem 1b. Yeah, I think what you're referring to is this how they exist and the truncation interact. So yeah, I think that's what, part of what we proved in 1b. Okay, so so now we can proceed with this where X is equals fin of n. Okay, so so let's go ahead and dive into this proof. So the main thing I'm going to need, or one kind of further thing I'm going to need. So now that I'm assuming that X is fin n, then that gives me that this function f that I'm given goes from fin n into y. And so what I'm going to assume I can do is that so remember that fin n here, that's the type of 0, 1, all the way up to n minus 1. So if I have some m, which is less than n, then I can what's called restrict f to fm, which is going to go fin m into y. And so fm is going to agree with f on everything up through m minus 1. And so so we'll have f of fm of 0 is defined to be f of 0, fm of 1 is f of 1, and all the way up to fm of m minus 1 is f of m minus 1. So that'll be useful in this problem. Okay, so let's look at so that with that. So we're given that y has decidable equality, and we want to construct this. So we want to say for every y, either it has either we want to come up with a element of its pre-image, or we want to come up with a proof that there is no such element. And what we'll do is so what we'll do is we will so we want something of this type. We want for all y either is in this or not that. So so let's say we're given y and y. So now we want to construct something of this type. And so what we're going to do is we're going to essentially pattern match on whether y is hit by f. So think about this. Or wait. Yeah. So we have this y, and yeah, we want to show something of this type given the f. And so what we're going to do is we're going to do induction on n, which is the size of our x. So we assume that x is some we assume that x is some fin n. So n is the cardinality of x. And so let's do induction on anything that n might be, and then we're going to prove this claim by induction. And so our base case is that n equals 0. And so what we need to show is that so then if n equals 0, then our f, remember f goes from fin n, which is x, into y. And so f goes from fin 0, which is the empty set, or the empty type, into y. And so we need to prove that either y is in the image of f, or y is not in the image of f. And so clearly y is clearly there's nothing in x here which maps to y, because there's nothing in x at all. And so we're gonna go for the right hand side here. And so we need to write something of type there exists x in empty set such that f of x equals y, and we need to prove not that. So we want to prove that there is not anything in the pre-image of y. So if there were something in the pre-image, that would imply a contradiction. And this is a proposition, so we can. So remember, this is a truncation, and so we can assume we get access to this x and this p such that it says that f of x is equal to y. So we're taking this out of the truncation because we're mapping into proposition, and we can do that. And so then if we have this x, then we're just going to map that to x, because x is in the empty set in this case. So there we proved not. So this is a proof of so this is all proof of not inverse image of f at y. And so then in order to and this is for each y, and so then we just need to stick that in right into this coproduct, and then that's for each y. And so we've proven it for the end circles. All right. If there's no questions about that, then we'll go ahead and proceed on to the inductive step. So inductively, we're going to assume that. So now we're going to do the n+1 case. So our inductive hypothesis says that for any for any, I'll call it f prime from fin n into y, we have the inverse image of f prime to be decidable. So for all y and y, either in inverse image of f prime of y, or not. Inverse image of f prime of y. And so now, now we take some f from fin of n, fin of n plus 1 into y, and we want to show that this is decidable equality for f instead. All right, everyone clear on the basic idea here? So we have this, and we want to have this, and we want to prove that for all y, this, but for f instead of prime. Okay. And so now we're going to break into some kind of a little more complicated cases. So so remember, like I said a second ago, so if I have something from if I have a function f from a finite set into y, then I can restrict it to anything smaller. And so here I have a function f from the finite of n plus 1 to y, and so I can restrict that to fn from fin of n into y. And so this is going to end up being the f prime I want to use for the inductive hypothesis. Okay, so now what I'm going to do is I'm going to break into cases based on whether my and so now I want to prove this for given an arbitrary y in y. I want to prove in m f at y or not in m at y. Okay. And so I'm going to break into cases based on whether y, or I'm going to case on in m of fn at y. Or rather, so I'm going to use my inductive hypothesis. I can apply my inductive hypothesis to so I can apply my inductive hypothesis to fn, so that'll be my thing n, and then y, and so I have, so actually we can write this as IH, the inductive hypothesis applied at fn and fn and y. And so this says that so change color contrast. So IH of fn and y says that either in m of fn at y or not in m of f n. So either y is either y is in the inverse image of either y is in the image of fn, so there's something in the pre-image of y of fn at y, or there's not. And so I can break into these two cases. So case one is that IH of fn and y is equal to in left of some k, I guess, where k is in fn at y.
So, sorry, Jacob. Could you place the paper
Oh,
sheet
yeah,
a little
sure.
bit? Yes, a little bit.
Thank you.
Yes. Thank you.
Okay, so yeah, so this is a coproduct. So I do induction on coproducts, and so it's either it could be in the left case where yeah, so here K says that Y is in the image of Fn. So we want to prove yeah, we want to prove this. And so so here again we can so yeah, so if Y is in the image of Fn, then Y is going to be in the image of F. So if we remember in the inverse image is defined as this truncation of the fiber. So so you can check that this here is going to be a proposition, because this is a proposition, this is a proposition, and they're disjoint propositions. They can't both be true. So in general, the coproduct of two propositions is not going to be a proposition, because 1 + 1 is 2, which is not a proposition. But if these are disjoint, if they can't both be true, then their coproduct is going to be a proposition. So that's a useful fact. So we want to map it into this, and so we can do so. Since we're mapping into proposition, we can unpack this K, and so we get a so K, remember, is the yeah, so an image is the truncation of this fiber, and so we can assume that we have the X and the P of, I'll just write it as fib fiber of Fn at Y. So P says that that Fn of X is going to be equal to Y. And so then this gives us so then we can make so if Fn of X is equal to Y, then F of X is equal to Y, right? Because that's how this yeah, that's how this yeah, so X here is an element of fin n, and so if it's in fin n, then the restriction says they agree, and so we have that F of X is equal to Y. And so then we can repackage this to get something of type in F at Y. So that's the kind of easy case, is that yeah, the one of the first n things in bin n, if I apply my F to it, I get Y, and so then I'm done there. Okay, but moving through the second case, then yeah, then I have so now case 2 is that IH of Fn at Y is the right thing. So the right thing is that not this. So this is so that it's in right of I'll call it L. And so L says not in of Fn. So this says that that all the so of all the things that are hit by Fn, Y is not one of them. So we can prove that the fiber of Y is empty. Okay, so so now we need to again break into two cases, and these two cases are going to be provided by this decidable equality. So we haven't used this yet, so we'll need to use this. So we assume that Y had decidable equality. So what that says is that for any two y and y prime, then either they're equal or they're not. And so what I can do, so what L tells me is that f of 0 is not y, f of 1 is not y, ... all the way to f of n minus 1 is not y. And so the last thing to check on is whether f of so it's a different color. The question is f of n equal to y? So we know that not f of 0 equals y, assuming here n is n is bigger than 0 or whatever, but and we know not f of 1 is equal to y, ... all the way up to f of n minus 1 is not equal to y, but is f of n equal to y? So that's all that's contained in here, but is f of n equal to y? And so if I apply my decidable equality for y to f of n and y, then that's going to say that either that's going to give me proof that either f of n is equal to y, or it's going to prove that f of n is not equal to y. So there's where I'm using the decidable equality of y. And so now what I'm going to do is I'm going to break into two cases on this. So this is within my case here, is f of n equal to y. So then so let's break into these two cases. So case 1 is that dec EQ of f of n and y is the left thing. So is in left of q, where q says that f of n is equal to y. Well, then this is again easy, because if f of n is equal to y, then I have an inhabitant of the fiber of y under f, namely n. And so I can say that, so I can take n, and so I want to give something of this type. So I can take n, which is a term of type fin n plus 1, and I can take my q here, n and q, and I can put them through the truncation process. And so this is going to be a term of type the truncation of n in fin n plus 1. Oh, sorry, this is that's fine. Such that f of n, or I just want to call this x, x equals y. So this is in this truncation, which is exactly the same thing as inverse image of f at y. And so if I stick it in left, then I've proven this for that case. Oh, sorry, I missed a question a few minutes ago about could you recall the definition of disjoint? Yeah, when I said things are disjoint, I mean that they can't both be true. So in particular, particularly whenever you're dealing with these kind of decidable things, this proposition is this is always going to be a proposition if both of these are propositions, because they can't both be true. This type of a proposition plus its own negation is always going to have at most one element, because either this is inhabited and this isn't uninhabited, or this is uninhabited and this is inhabited. And so if they're both propositions, then there can only be one. So that's what I mean by disjoint, is that they're not both true, or they can't both be true. Okay, so that's the one case, is that if this decidable equality tells us that f of n, or that tells us that f of n, if f of n happens to be equal to y, then I again have found that something in the I've again inhabited the preimage of f of y. Otherwise, the other case, that dec eq of f, n, and y is in right of some nq, where nq says that not f of n equals y. So f of n is not equal to y. And then here, what I'm going to do is I'm going to prove that not in the image of f at y. And the reason I'm going to do that is because I've exhausted my domain here. So my domain here, so again, f goes from fin of n to y. And so I proved up here that f of 0 is not equal to y, f of 1 is not equal to y, and so on, all the way up to f of n plus, or f of n minus 1 is not equal to y. And then finally, I've gotten one more thing that says that f of n is not equal to y. And so I can package that all together to say that, I can essentially say that for all x in fin n, not f of x equals y. And so from that, using that, then I can, since this is a proposition, I can use that, but I'll kind of leave this to for you to try out on your own, because I'm out of time. But yeah, you can check that that this will allow you can use the recursion principle for propositional truncations to show that given that, you can construct a proof that if you had something in the image of if you had something in m of fy, then that would cause a contradiction, because you proved that that it can't be 0, can't be 1, can't be all the way up through n, and so there's nothing it could possibly be. That's what this says. And so from there you can construct a contradiction from in fy. Okay, I'm gonna have to cut it off there. So I'll have to refer you to just the solutions, the written solutions for part 6b, and then all the other questions. Like I said, Artem I think got through, gave an explanation of the rest of 1 and I think 3 and 4. So and I think 5a. So that's also there for your reference. But I think I'm going to go ahead and stop the recording. And thank you all for coming.